Detecting Follow-up Recommendations in Radiology Reports with Transformer Architectures. This work is done by Robert Liu, Sadhana Ravori, Satyarth Vaidya, and Tian Pham. First of all, what is a radiology report? Here we see medical imaging that has been read by a radiologist. They document their findings, and then they come up with a clinical impression. In this case, this is a normal CT sinus. However, sometimes they find suspicious findings, and then they would recommend follow-up imaging or follow-up with a doctor. We have found that 35 to 50% of patients who receive follow-up recommendations for possible findings of cancer do not return for a follow-up, and thus they remain at risk for missed or delayed cancer diagnosis. If we could automatically find these follow-up recommendations in radiology reports, this would allow us to better track patients who need follow-up. What other work has been done in this area? There's only one other deep learning work on the same task. In their work, they trained an LSTM, however, their LSTM did worse than their logistic regression. In the broader clinical realm, there has been work in pre-training a BERT model on the MIMIC3 dataset. The MIMIC3 dataset is a clinical notes dataset. However, this differs slightly from radiology reports. There was also another paper pre-training an XLNet on the same MIMIC3 dataset. It's important to know that radiology reports often contain a lot more anatomical vocabulary as well as measurements that makes it different from clinical notes. So for our own work, we gathered 6,000 reports from the Hospital of University of Pennsylvania. Unfortunately, this dataset is not publicly available, and we all had to perform city training to access the data. It's notable that this dataset only contains 13% follow-up recommendations, and thus is very imbalanced. We also note that most reports are quite long, and in fact they're longer than 512, which is the max sequence length for the BERT model. So how did we address these? So a priori, we thought the clinical BERT architecture would be best since it's pre-trained on clinical notes. In our architecture, we take the radiology report and then we pre-process it by stripping out the impression section. With that impression section, we tokenize it into word piece tokens, which are then fed into the BERT architecture. This then spits out a size 768 class label, which we use in our classifier network. This is a simple, fully connected linear layer which outputs a logit. For our loss function, we use weighted cross entropy because our dataset is imbalanced. In sum, this is around 110 total parameters that we are adjusting. So after all the training, here are our results. We trained 4 traditional machine learning models, as seen here, and the best one was logistic regression with an F1 score of 0.567. Then we trained an LSTM. This showed improvements with an F1 score of 0.645. Then we used our advanced deep learning methods. We used BERT, clinical BERT, as well as 2 implementations of XLNet. The best performing model was BERT. Notably, it seems that clinical BERT, after being pre-trained on the MIMIC3 clinical notes, did not improve on BERT. To look into that deeper, we note these performance metrics. In the medical world, we often want sensitivities above 90%. That means we're catching 90% of the positive cases. So in this precision recall curve, we can see that we want to be in this region here. However, that means that our precision would be around 50%. That is, half of our positive calls would be wrong, but we would still get 90% of the positive cases. Ultimately, current performance is not robust enough for clinical usage, but we think that the 3 challenges we faced can be overcome. The first is radiology language. Because clinical BERT didn't improve on BERT, we think that the radiology language is different enough from clinical language, such that pre-training on a radiology text corpus would help. This would allow us to better separate our classes, which, as we can see, are not very separable. We also think that if we had a larger data set, we'd have more positive examples, which means more training data. Because of our imbalanced data set, we didn't have that many positive samples. And finally, because of the reports being very long, we think there are better ways to deal with this than just snipping out the impression section. We could generate a summary of the report, or we could process each sentence individually and pull results, though this would be computationally more expensive. Ultimately, these fixes would improve performance and potentially make this system more clinically useful, which was our original intention.